Welcome students. Let us revise some of the concepts that we have learned earlier and solve a few of the problems for our entrance exam. First problem we have: at which temperature is RMS speed of hydrogen molecules the same as that of oxygen molecules at 1327 degrees centigrade? We have learned this about the velocity of the gas molecules earlier, maybe in the second year BSc, and we have learned about three types of speeds: root mean square speed, most probable speed, and average speed. Okay, and Maxwell also has given us the formulas to find out these three speeds. Now, one of the Maxwell formula to find out the root mean square speed is RMS is equal to square root of 3RT upon M, where R is the gas constant, T is the temperature in degree Kelvin, and M is the molecular weight or the molar mass. So that also has to be substituted in kg, okay, kg per mole. So we know that there are two gases now in this problem. We have oxygen gas and hydrogen gas. Molecular weight of oxygen is 32 grams per mole. Multiply by 10 raised to minus 3, you will get kg per mole. Similarly, we have the molecular weight of hydrogen gas, which is equal to 2 gram per mole. Multiply by 10 raised to minus 3 kg per mole. Now, when will the two speeds be equal? At what temperature will the two speeds of the two molecules be equal? So you have to find out the temperature. So if you look at the problem, we are given the temperature of oxygen molecules, and we have to find out the temperature of the hydrogen gas molecules. So the temperature of the oxygen is 1327 degrees centigrade. You have to add 273 to that particular temperature. So we have, when you add 273 to that temperature, you get it as 1600. So here we write, say one side, the hydrogen gas, when will it be equal to the root mean square speed of the oxygen gas. Hydrogen gas, when it will be equal, at what temperature will it be equal? So substitute the formulas: 3RT upon N. So if this side is oxygen, I will write this as TO, temperature of oxygen, and molecular weight of oxygen. Similarly, this side we write 3RTH upon MH. TH is the temperature of hydrogen, and which we have to find out, divided by the molecular weight of hydrogen. So if I substitute these values, now my 3R this side will cancel with 3R from this side, and square roots also will cancel out. So what remains is T0. T0 is 1327 degrees centigrade plus 273, which gives you 1600 degrees Kelvin. So we have T0 here. This T0 is 1600 degree Kelvin divided by the molecular weight of oxygen is 32 into 10 raised to minus 3 is equal to, this is what we have to find out, the temperature of hydrogen, and molecular weight of hydrogen is 2 into 10 raised to minus 3. So if you solve this, you will get pH is equal to 100 degree Kelvin. The second question we have: at constant temperature, the slope of the plot of PV versus volume is dash. Suppose you are given an option of 0, 2, 0.5 and 1. a graph of PV versus volume is constant, we have to know that is Boyle's law. PV is equal to constant. So PV remains constant. So the slope of this type of a line will be 0. So we have this particular option. So we have, this is our answer. So here you have to remember Boyle's law. Third one, we have the density of an ideal gas is given as P upon V NP Pm upon RT P upon RT. So ideal gas equation, we have PV is equal to nRT, and we have another form of that equation which is the density version, that is where density is involved. That is Pm is equal to dRT. So D will be equal to Pm upon RT. So our third option is there, Pm upon RT is the density of an ideal gas equation. You could also be asked to calculate the density of an ideal gas equation if you are given pressure, molecular weight divided by if you are given the temperature and you know the gas constant. The next question for you is, for ideal gas, a graph of pressure versus volume at constant N and temperature is this particular curve B. It is a smooth curve. The next question would be the working electrode in the determination of pH of an acid solution using quinhydrone powder is which electrode? Usually we use two electrodes. One is the standard calomel electrode, that is a reference electrode. So the working electrode is a quinhydrone electrode. Though we put a platinum electrode, it is not an electrode as such, it is just a platinum wire that is only used for electrical contact. So the electrode that is formed in the solution, that will be your electrode, that is your acid solution with the quinhydrone powder forms the quinhydrone electrode. Okay. The half-life of a second order reaction with initial concentration of the reactant as 0.2 molar and rate constant as 4 into 10 raised to minus 3 moles per mole per second is dash, the half-life. So half-life you have to calculate. Okay. So how do you remember the formula? This is for second order reaction. So for second order reaction, say with initial concentration, we have K is equal to 1 upon AT into X upon A minus X. When the amount reacted is A upon 2, half the initial concentration is equal to half the initial concentration, time is taken as T half. So if you substitute this in the above equation, your K becomes equal to 1 upon A T into X. X is A upon 2 divided by A minus X. A is A upon 2 minus X. Okay. You can do this quickly. So then we have, this is 1 upon AT into A upon 2 divided by A upon 2. So we have the numerator and the denominator cancelling out, and sorry, we have missed out here. This is half. It becomes half-life, right? So K is equal to 1 upon A into T half, or you can write T half is equal to T half is equal to 1 upon A into K. Now, if you take this formula, T half is equal to 1 upon A into K and substitute. Initial concentration is given to us as 0.2 into, you are given the value of K into 4 into 10 raised to minus 3. If you 1 upon, okay, 1 upon. So if you work this out, it works out to 1250. Since it is T half, it has units in seconds, because the units here which are given are in seconds. I want you to remember the potentials of the calomel electrode. Calomel is used as a secondary reference electrode. Hydrogen electrode is our primary reference electrode. So the representation of the calomel electrode is given in this way. It is mercury in contact with mercurous chloride, which is also called as calomel, which is a solid, and which is in contact with 0.1 normal KCl solution. In this case, then the potential would be minus 0.3538 volts. If the concentration of the KCl here is replaced by 1 normal KCl, then the potential will be minus 0.2800 volts. And if the concentration of KCl is replaced by saturated KCl, then the potential of the electrode would be minus 0.2415 volts. And this is what we use in the laboratory. In the lab, we use saturated KCl for the calomel electrode. It is dipped in saturated KCl solution, and the potential we all know, it is the oxidation potential minus 0.2415 volts. This electrode comes under metal insoluble salt electrode. Metal, this is our insoluble salt, and it has a common anion, so Cl minus to that of the salt. So Cl here and Cl here. So common anion electrode. The next question for you is, the rate constant for a reaction is 2.5 into 10 raised to minus 3 minute inverse. What is the order of the reaction? Sufficient information is given, but we may be a little confused. If you look at the rate constant for the reaction is given by 2.5 into 10 raised to minus 3 minute inverse. From this unit that is given to us, minute inverse, we know it is the unit of rate constant for first order reaction. So without doing any calculation, you can say it is a first order reaction.